get the Lagrangian formula, that equation, right? So in Hamilton's principle, we are considering an integral equation, and by using that, we are deriving the Hamilton's equations of motion. And one other difference is that in the first one, that is the D'Alembert's principle, we make use of the forces. In order to describe the motion of a particular system, we make use of something called as a force. But in Hamilton's principle, what happens is that we are not describing the particular motion of our system by terms of force, but rather another quantity called action or action interval. So we need to understand what an action interval is and many other fundamental parameters in order to understand this principle. So this is nothing but just a normal principle with a mathematical equation. Okay. So for understanding this, or by using this principle, we can actually describe the motion of a whole system. Okay. So for understanding this particular principle, we need to have an understanding of all these things. So the first one is action interval, second one is a conservative system, third is a monogenic system, holonomic system, and configuration space. Okay, so I think action integral is new to us. All other things are something which we already know, right? So what is a conservative system? Something is conserved. That means that it is a type of system wherein if we have a lot of forces acting upon a system, all such forces are conserved, or there is no loss of energy for that forces. Or we can say that the total energy, that is the kinetic energy and the potential energy, remains constant. So that is a conservative system. The next one, that is a monogenic system. So do you know what is a monogenic system? That means that it is a type of system wherein the forces acting over a system is derived from a single potential energy function. All the forces acting over a system is derived from a single potential energy function. So that is the monogenic system. Next is holonomic system. So you have something called as holonomic constraints, right? So what was that? It could be written in terms of equations, right? So holonomic constraints are something which could be written in form of an equation, and the systems which possess such kinds of constraint forces are basically what we call a holonomic system. Okay. Next is the configuration space. So what is the configuration space? Configuration space. It is basically a system, it is basically a space, an abstract mathematical space, wherein each of the point represents a specific arrangement of the system. So if we have to describe a particular system, we need coordinates, right? So for example, if we have one coordinates represented to denote the motion of a system, the corresponding configuration space would be one dimensional. Okay, so in the similar way, if it's two coordinates that represents a system, it is two dimensional. In the similar way, if it is n coordinates, then n dimensional. Okay, so we will come to action integral in detail because that is something which we need to know for understanding this principle. So for that, let us consider a scenario. Okay, so let's suppose here you can see a child is throwing a ball. Okay, sorry, a stone. Okay, so what happens is that if a child is throwing a stone from a particular point, let's suppose point P. Okay, and from point P, the child is throwing a ball so that it reaches point Q within the time interval T1 and T2. Okay, so the child is standing at the point P. He is throwing a stone so that it reaches the point Q. So normally there is like a lot of paths which could be possible for the stone to travel, right? So but nature always chooses a single path. Do you know what is the reason? Is there any condition criteria? Yes, right? Because for example, like if we have to reach Sabarmati, we always use the shortest path, right? We never go around, or rather, what is the main parameter behind that? We always want our energy to be bare minimum. So that is the main reason why we are choosing a shortest path. So in the similar manner, nature always chooses a path where there is a certain parameter called action that becomes stationary or minimum. Okay, so that is the reason why that path. Out of all these paths, it could either go in a straight line, or it could travel in a curve, or in a zigzag manner, anything. nature always chooses a path where the quantity called action is stationary or minimum. Okay, so next is these are some things which I've explained. Now, if we have to choose a path, let's suppose we can name this path as 1, 2, and 3. So, in this path 2, let's suppose the stone is at this position. So, over this position, the stone possesses both kinetic energy and potential energy. Okay, in the similar manner, if the stone possesses both kinetic energy and potential energy, it consists of a corresponding Lagrangian, right? So, what is the Lagrangian? Kinetic energy minus potential energy. So, will that Lagrangian be similar to the stone if it is positioned somewhat over here in the same path? Like, will the value of Lagrangian will be same in the same path if it is somewhere over here? It will change, right? Because the corresponding kinetic energy and potential energy will change. Thereby, the value of Lagrangian will also change. So, if we have to find the Lagrangian of this whole part, what will we do? Integrate. Okay, so that is the main principle. If we have to find the Lagrangian, we have to integrate within the time interval t1 and t2. So, if we have to find the Lagrangian of this whole part so that the stone is traveling, we have to integrate it from the time interval t1 to t2 L dt. Okay. This is what we call action. Okay, it is denoted by S. In some cases, it is denoted by I. Okay. So this is what we call action or action interval. Okay. So as I said, action interval is the time interval of the Lagrangian. It is the time interval of Lagrangian, and it assigns a value to each possible path of motion of the system. Next one is conservative system. These are some things which I already told. So there is a condition, if a system is conservative, you can say that the force would be the negative gradient of potential. Now what is a monogenic system? Which could, all the forces acting over a system is derived from a single potential energy function. Such kinds of systems are called as monogenic system. So here we can say every conservative system is a monogenic system. Okay. Configuration space. Now we can move on to, we know what is an action interval. This is the action interval. Then we understood what is a conservative system, holonomic system, configuration space, and we understood about monogenic system, action interval, conservative system, holonomic system, and configuration space. So I hope it is clear. So if we understand till this point, we can understand what is the statement of Hamilton's principle. It is quite simple, as I explained. Before that, if we have to explain the motion of a particular system using the Hamilton's principle, we have to consider many cases. That means that the system considered would be a conservative system. Conservative system, then this must be a dynamical system. Dynamical means which moves, right? Dynamical system, and it is a holonomical system. And this particular motion is represented over a n-dimensional configuration space. Okay, so this particular system is represented using a n-dimensional configuration space and over the n generalized coordinates. Okay, so if we have to define the motion of a particular system using the Hamilton's principle, we need to consider a system that is conservative, dynamical, holonomical, so that we can describe the whole motion over an n-dimensional configuration space corresponding to n generalized coordinates. Okay, so this is the main criteria before we go on to the principal statement. So the statement is, it states that the actual path followed by a conservative, holonomic, dynamical system over a fixed time del I, right? Del, this is represented as S or I. So we can write del S. And this Lagrangian is basically a function of the coordinates, velocity and time. So as I said, the coordinates are n generalized coordinates, right? So we can write, this is q dot velocity and time. So integral t1 t2, L could be written as a function of generalized coordinates q1 q2 qn, and velocity again could be written as q1 dot q2 dot qn dot and time. If we take the variance, a variance delta sign would be applied over here also. So it would be integral dt equal to 0. Okay, so this is the mathematical equation and that is a simple statement. So the thing is, the one actual part is the one where the Lagrangian, the time integral of Lagrangian is either maximum or minimum. Okay, and if we take the variance, we write the Lagrangian as a function of the coordinates, velocity as well as time. That becomes 0. Okay, so this is the condition. Next is the consequences of Hamilton's principle. What exactly is the benefits of using this Hamilton's principle? First thing is that we can derive the Hamilton's equations of motion using this Hamilton's principle. So that is the first consequence. Second one is that it provides a unified treatment for mechanics. Like we can describe any sort of system, be it a rigid system, a particle, or a system of complex identities. We can actually describe everything in a unified manner. So that is the next consequence of using this principle. The third one is it handles constraints easily. We do not have to explicitly mention constraints separately. This particular principle takes into account constraints in a unified manner. So first one is a derivation of Lagrange's equation. Second one, it gives a unified identity for mechanics. Third one, handles constraints easily. Next is connection to conservation laws. It basically describes about and its relation to symmetry. I think that has been taken by Anita. So the thing is, this principle also takes into account the conservation laws. Another one is leads to Hamiltonian mechanics. So this particular principle leads to a completely different branch of mechanics called Hamiltonian mechanics. And it gives a basic modern foundation for the modern physics. Okay? And again, this is what we call the least action principle. This particular principle is also called as the least action principle. That basically describes why nature always chooses a certain path by means of certain optimization condition. Okay, which I have described about the quantity called action. The path in which action becomes minimum or maximum, that is, it becomes extremum, that is the specific path the